Okay, let's wrap up here with summarizing how this works, right? The table shows the property of a wave on a beach one summer day. The relationship between speed and wavelength and frequency, we're going to use the relationship between speed, wavelength, and frequency to complete the table. Okay. So let's start by completing the table. You're going to fill in speed, wavelength, and frequency here using this equation. Okay, so we start with speed. So we can calculate speed, right? It's wavelength times, or wave speed is equal to wavelength times frequency. We've got a wavelength of 10 meters. We've got a frequency of 2 hertz, or 1 over s, right? If we multiply those, right, we get 10 times 2, that's 20. And we get meters times 1 over s. We can rearrange that. We get 10 times 2 is 20. And now we get meters per second. So our frequency, or our wave speed, is 20 meters per second. Okay? And here I'm reminding us that hertz is equal to 1 per second. Okay? Okay. Next, you should have filled in 8 meters. We got to that by saying that our speed of our wave was given to us at 32 meters per second, right? Our wavelength was unknown initially, and our frequency was 4 hertz, or 4 per second, right? So we're going to take this 32 meters per second, and we're going to divide both sides by its frequency. So we're going to take the 4 hertz, 4 per second, and divide both sides by 4 per second. That's going to, on this side of the equation, that's going to cancel out the 4 hertz, because you're dividing 4 hertz by 4 hertz, right? On the other side, we're going to go ahead and work this operation, right? So I'm going to rewrite that really quick just so that it's clear, right? We got 32 meters per second divided by 4 hertz is equal to wavelength. Okay. So we're going to rearrange this so it's a little bit easier to work with. We got 32 divided by 4. 32 divided by 4 is 8, right? Times meters per second divide by per second, per hertz, okay? Okay, so I don't know if you played around with this too much or not, but if you take 1 and divide it by 1 divided by s, you get s on top. So we're going to take the s that is on top, so we're taking 1, divide by 1, divide by s. We're going to take the s, divide by s, and we're going to cancel the s's out. So we end up with meters, right? So we get 8 meters as our wavelength here. If you're having problems with that, pull me aside and I can work through the math on that. Okay. For our last one, we want to solve for frequency. We got wave speed equals wavelength times frequency, right? We know that it's 36 meters per second, that's its speed. We know that its wavelength is 12 meters, and we want to solve for frequency. So we plug those in. We get 36 meters is equal to 12 meters times frequency. We're going to eliminate the 12 meters from this side so we can isolate frequency. So we're going to divide this side by 12 meters. If we do that on the right side, we want to do it on the left side too. So we're going to divide both sides by 12 meters. Okay. So we're going to cross out the 12 meters on the right. Okay. So that's going to simplify our equations to 36 meters per second divided by 12 meters equals frequency. Okay. We're going to rearrange this equation around a little bit, and we're going to say that 36 divided by 12 times meters per second divided by meters is equal to frequency. Let's see how that works out for us, right? 36 divided by 12 is 3, so 3 times 12 is 36, right? 1 times 12 is 12, 2 times 12 is 24, 3 times 12 is 36, right? If we take meters per second and we divide by meters, we put the meters divide by meters are going to cross out, so you get 1 over s. So you end up with 3 per seconds, right? Or 3 hertz. So its frequency is 3 hertz. So we write down 3 hertz up here. Okay. Now, if the amplitude of the wave at 6 p.m. increases to 6/10 of a meter, right? How many times greater would the energy become? Okay. Remembering that we're going to use this proportionality. The energy is proportional to the amplitude squared, right? And proportional is this little symbol here. Okay. So, I'll give you a second to work on that. Okay. So we start with 6 p.m. The original wave was 3/10 of a meter. That's how high it was, right? Its energy is proportional to that number squared, so we're gonna multiply 0.3 times 0.3. We can write that as 0.3 squared, right? And that's joules. And we're going to end up with 0.09 joules, proportional to 0.09 joules. At 6 p.m., if we adjust it, if we increase the amplitude to 6/10 of a meter, right? Then we're going to get 6/10 times 6/10, or 6/10 squared, is 0.36 joules. Okay, so now the question is, so we know how much it was initially, right? And we know how much it increased with our adjustment. Now we want to know, well, how many times was this bigger than the old one? So we're just going to divide 0.36, our new result, by our old results to see how many times bigger 36 is than 0.9. How much bigger is 0.36 than 0.09? That's right, it's 4 times bigger, right? Okay. Use proportional relationships. Recall that wave speed and wavelength is equal to wavelength times frequency. And energy is proportional to its frequency. Assuming that we took a wavelength of a wave system stays the same, so the wavelength is going to stay the same, would the energy of the wave increase or decrease if the speed of the wave increases? Why? Put that in a paragraph. So we want the wavelength to stay the same. We're going to increase the wave speed. What's going to happen to the energy of the wave if we go ahead and increase the frequency? With our wave speed equation, we know that wave speed is equal to wavelength times frequency. We know that if the wave speed increases, then the combination of wavelength and frequency must also increase. Here we've required that a constant wavelength. This means that we have to have the frequency increase, right? The equation tells us that. We also learned earlier that wave energy is proportional to the frequency of a wave. As a result of these conditions, energy must increase if the speed of the wave is held constant. If the speed increases, even if the wavelength is held constant.